Okay, so I thank the scientific organizers to give me the opportunity to talk here, and I shall be talking about Born approximation and the spectrum of primary gravitational waves at high frequencies. By high frequency, I mean gravitational waves of wavelengths which are smaller than the Hubble radius at the end of the inflation. So this talk is based on our ongoing work with Olive Prio, Professor Jerome Martin, and Professor Sriram Kumar. So first in the first two slides, I shall talk a little bit about the inflation, primary gravitational waves and adiabatic regularization that Olivia already covered, but just for completeness, I will show the expressions. And then I shall go into the main part of my talk, which is about Born approximation and connection between the behavior of the regularized spectrum and the evolution history. Then I shall show a few smoothing functions and show how the behavior of the regularized spectrum is changing with the different choice of smoothing functions, and then I shall conclude. So as we all know, inflation is an accelerated expansion at the start of the universe, which lets the quantum fluctuations to go beyond the Hubble radius classicalize and give the initial conditions for the inhomogeneities of the universe that we observe in the CMB anisotropies and the large scale structure that we see around us. In this talk, we are only interested about tensor perturbations, which is actually the perturbations on the metric, the transverse and traceless part of the metric. And if we go to the first order perturbation in the Einstein equation and use the Friedmann equations, we can get this equation of motion for these tensor perturbations. And if we rescale the Fourier modes of the Hij by a scale factor, then we get this Mukhanov-Sasaki kind of equation with the effective potential of A double prime by A. The spectral energy density in terms of this Mukhanov-Sasaki variable is given by this expression. During radiation domination, the Mukhanov-Sasaki equation, this A double prime by A is actually just 0 because A is linear in conformal time in radiation domination. So we get just a harmonic oscillator expression, and then we can expand it in terms of e to the power plus I k eta and minus I k eta. And if we put this mu k inside this expression, then we get this spectral energy density expression, which is proportional to y to the power 4 into 1 plus beta by A square, where y is proportional to k. And as Olivia already discussed, if we do the adiabatic subtraction, we get this expression, this 1 is gone, and now it is only proportional to y to the power 4 into beta by mod A whole square. So now as we already saw, solving the whole equations and for the mu k for the all the expansions and matching all the mu k and mu k primes at the different transition points, it is difficult to do. However, as we are only interested in the k very greater than k, where k is the mode which exists the horizon at the end of the inflation. In those ranges, actually you can put the effective potential part in the right hand side and treat this as a perturbation, because k is very greater than k, and the maxima of this effective potential is actually of the order of 2 by eta square. You can easily check it by the de Sitter phase, because it is 1 by eta square, and at the end of the inflation it is just 2 by eta square. And also I will show the plots of the different choices of the effective potential, and we will show that all of them are of the order of 2 by eta square. So we can use this as an perturbation on top of this expression, and if we do that, then we can use the Born approximation, and then we get the expression of mu k like this, where mu k 0 is the solution of this expression when the right hand side is 0, and g is the Green's function where we get what we get from this equation of motion when the right hand side is replaced by a delta function. Now if we put the Green's function in the mu k solution at the first order Born approximation, then we can write this as a linear combination of e to the power plus I k eta and minus I k eta, just like the radiation domination scenario that I discussed before. And then we can identify the alpha and betas from this expression, and if we do that, the beta comes to be just like this. So it is just an integral of u with multiplied by e to the power minus 2 I k eta prime. So we do not need to go to the solution of the whole mu k. We can just calculate the beta k and use this expression of the regularized gravitational waves in terms of beta k and y to get the behavior of the spectral energy density at small scales. Now I shall show the first two parts that Olivia already showed, which is about the abrupt transition and the linear transition. For abrupt transition, here I am only using the de Sitter phase. So for abrupt transition, the u goes as 2 by eta square, and if we do the integral for the beta, then we can write it. We get this expression, where at leading order it is actually going as 1 by y square. So if we put it in the spectral energy density expression, then it is proportional to k to the power 4 into beta by mod s square. It is actually scale invariant, as Olivier already showed. And if we go to the linear transition, where we put an extra epoch with a effective potential which is linear in conformal time, if we put that inside the de Sitter and the radiation domination phase, then we get an extra contribution from this linear interaction, linear U phase. And if you look at it carefully, from the inflationary part, the expression that we got for beta, and from the smooth linear transition part, that the expression that we got, the first terms actually cancel out, completely cancel out. So if we add both the betas and we calculate the total beta E, it is actually going as proportional to 1 by k cube. So the spectral energy density goes as 1 by k square, as Olivier already showed. Now we can go one step beyond. We can try with a quadratic smooth function. If we do that, we have one extra parameter on top of the linear function. So we can either choose the u prime to be continuous at descent or at descent. We have done both of these. If we do that and calculate the beta function, calculate the beta, the integral of the beta, then the first term of the beta is actually same as the first term of the linear transition. So what we again get as the total beta is actually proportional to 1 by k cube at leading order. So we do not gain anything over the linear transition scenario. Now we can go to another scenario where we have the u to be a cubic function or a quintic function. Now we have, for the cubic case, we have two extra free parameters. Okay. For the cubic case, we have two extra free parameters, and for the quintic case, we have 4 extra free parameters. So for the cubic case, we can actually we can actually make the u prime continuous at both the end, and for quintic case we can make the u triple prime continuous at both the case on top of u and u prime. So if we do that, then if we calculate the integral of the beta, then we get 1 by k to the power 4 for the cubic case and 1 by k to the power 5 for the quintic case. So we get the spectral energy density of the behavior of the spectral energy density becomes y to the power minus 4 and y to the power minus 6, which is k to the power minus 4 and k to the power minus 6 respectively. Now we can go one step beyond. Up to now we are only using piecewise functions. Now we can use some function which is true for the entire time range, and one such choice is a Lorentzian kind of transition, where we have this 2 by eta square plus eta square, and for any non-zero eta value, it is actually the derivatives are continuous of this function at all orders. And however, the one thing is that it only imitates the de Sitter phase at the eta goes to minus infinity limit, but at eta goes to infinity limit, it does not imitate the radiation domination case that we were discussing up to now. However, if we do the integral, what we get is that there is an exponential term in the beta k. So if we also calculate the spectral energy density, we get actually y square into e to the power minus 4y, and y is proportional to k. So we get an exponential suppression of the spectral energy density at small scales. Now, as the last example that I showed, it was not imitating the radiation domination phase at large eta values. So we can go around that with a extra term of 1 plus tan hyperbolic function. If we do that, then it imitates the de Sitter phase at the early time, and it imitates the radiation domination phase at late time. And if we do that, then do the integral, then we again get a exponential minus 2k exponential minus 2k term. So the spectral energy density is actually again exponentially suppressed for this choice of u. Now this is the plot of the spectral energy densities that I was talking about. So the red one is the unregularized power spectrum, and I have plotted it for all the frequency ranges. However, as I already mentioned, for the Born approximation, if we use the Born approximation case, we can only show the spectrum for k greater than ke, because the Born approximation is only applicable for that range. So for the abrupt transition, we have this scale invariant spectrum. For quadratic and linear transitions, we have a 1 by k square kind of suppression. Then we have 1 by k to the power 4 and k to the power 6 for cubic and quintic, and then we have exponential suppression for the regularized spectrum for the infinitely continuous cases. So as we discussed, that there is a k to the power 4 growth of the spectral energy density as k greater than k, and it must be addressed with adiabatic subtraction. For k greater than k, the behavior of regularized spectrum can be calculated using Born approximation, and we observe that the behavior of the spectral energy density at small scales, it is actually dictated by the properties of U. I have given a small table of what I already discussed. For instantaneous case, the continuity is up to Hubble. However, the discontinuity starts from U, and we have a k to the power 0 spectral energy density. However, for linear case, we have a k to the power minus 3 for beta k, and it is continuous up to U, but discontinuous from U prime, and we have a k to the power minus 2 spectral energy density. For cubic and quintic, we have continuity up to U prime and U double prime, but they are discontinuous from the higher derivatives, and we get k to the power minus 4 and k to the power minus 6. And for infinitely continuous choice of U, we get a exponential suppression. And so the conclusion is, the more we smooth the transition, we get a stronger suppression of the regularized spectral energy density for k very, very greater than k. Thank you.
Thank you, Arnab. So you did excellently time. We have time for questions. I see a hand up there.
Hello. Thanks for the nice talk. Okay, I have a very quick question also, taking hints from the previous talk by Oliprio. As you were dealing with very short wavelength modes, spectral behavior, so while studying the behavior of the short wavelength modes like k greater than k, did you take into account the background oscillation effect? I mean the oscillation of the inflating profile?
No, the transitions there was no background model on it. It was just the de Sitter to radiation domination abrupt transition initially I showed. Then I had some functional forms, directly functional forms, not coming from some background physics. It was the study is about looking at the continuity of the function of U, not about realistic models. We will do it in a later work where if we deal with realistic scenarios, what will happen.
Okay,
but
so
realistic scenarios should be like infinitely continuous, and we should get exponential suppression in those scenarios.
okay, then what do you think if you consider the finite reheating phase, then we must take into account the oscillation profile of the inflaton during
Yes,
reheating. So
it
that
will-
may change that spectral behavior,
Yes,
I think.
that will definitely change. Yes, I already showed now for different transitions, you will get different kind of regularized spectrum. So you will obviously get
The
different.
envelope would probably be the same, right? Exponential suppression will be there. if
Suppression
it's-
will be the same, but there may be some around k equal to k. There may be some.
And this spectral index will also change depending upon the equation of state and oscillation profile also. Okay.